Okay, Chemistry 2341. Here's Chapter 7, Section 3. We're going to look at those same elimination reactions with alkyl halides, but we're going to use cyclohexanes to help us define what our products are going to be and show us kind of why some of these systems happen the way they do. Okay. So the first thing we're going to look at is when we have our cyclohexanes converting to cyclohexanes, we have to look at where the halogen is and where the hydrogen is. Remember, we want these to be opposite each other if at all possible, but that might not be possible in a cyclohexane because we don't have free rotation around that double bond. So what we have to do is we have to kind of find the best situation we have by having them not be completely anti to each other, but try to find a more stable configuration to make the reaction happen. So what we're going to look at is if we have our halogen in the axial position, that's going to give us our hydrogen is going to be as close to anti as at all possible to give us our possible material here. And we have two different axial hydrogens to be able to do that conformation. Okay. Now, if we have our equatorial hydrogen here, we actually don't have a equatorial halogen here. We have beta hydrogens, but neither one of them are going to be in that fully anti position. So not being able to in that fully anti position, it's actually going to be less stable for it to eliminate. Okay. So let's look at what that means is that in the case of our chloride being in the axial position, it is less stable for it to be in that axial position. However, now that the hydrogen is also in the axial position, that means it's anti to the chloride, which means we can undergo an E2 elimination because the hydrogen and the leaving chloride are anti to each other. If we actually have it go back and forth such that the chlorine is in the equatorial position, we do not have a hydrogen that it can be anti to. We can only have hydrogens that'll be a little bit offset, a little gouged to each other. And as such, even though this conformer is more stable, it will not undergo that E2 reaction. So it won't undergo the E2 action because the hydrogen is not anti to the leaving group. Even though the less stable axial chlorine is less stable thermodynamically, it actually will allow an anti-elimination of the hydrogen from it. Okay, so let's look at that again and look at other ways to do things. So we can complicate the materials a little bit by having a large group on there to make it so it's even less possible for it to form that anti-configuration. Okay, so let's look at this first one right here. If we think about it here, this T-butyl group here is really big and bulky. It's bigger than this chloride is, so it's going to want to be in this axial position. I'm sorry, equatorial position. Because it's actually forcing it to be in this equatorial position, that's making the chloride and the halogen anti to each other, which means it's going to more readily undergo elimination than if it did not have this T-butyl forcing it to be in that group. So because this is a much less stable conformer, this one actually does not undergo elimination reaction, okay? So when we have this isomer such that we have the T-butyl group allowing for the chloride to now be in the axial position, the equatorial position instead of the axial position, we actually make it really, really hard for this T-butyl group to be in that axial position to give us these two in the anti configuration, meaning that this right here reaction is going to proceed much more slowly because of it cannot remove the hydrogen over here. So notice that it's going to give us the less stable axial position, which is going to give us the double bond in a different location. Notice here we're going to get the more thermodynamically stable tri-substituted alkene because of the position of this T-butyl group forcing the hydrogen, this hydrogen not to be anti to it, but allowing this hydrogen to be anti to it will make it such that we get this less stable di-substituted alkene during the elimination process. So this happens a lot when we have that big bulky base. And when we see it with the cyclohexane, we can help it look at it as helping us to decide which kind of Zaitsev rule product you're going to be getting. Okay. So the eliminated hydrogen is not necessarily the one on the beta carbon with the fewest hydrogen as the Zaitsev rule. So when we have this stability of the chair-chair configuration of the cyclohexane, we end up having a possibility where we get the not Zaitsev rule product because we cannot make it in the anti position. So we actually will end up with products that are outside of the Zaitsev rule. So another example of that, instead of just the T-butyl group, we're going to look at one with just a methyl group here. Even though this is the more stable conformer of the material, this does not allow for elimination across these two hydrogens because of where the location is, but we do have the two hydrogens over here, which will allow elimination across those hydrogens to give us our less substituted alkene because of the location of the methyl group. We have the less substituted alkene forms and not the more substituted alkene. Okay. So what happens if we have two alkyl halides in the same compound? Okay. So, and we have enough base that we can dehydrate either one of them. Okay. So we have a couple different possibilities here. And for example, we have, this is a 3,5 dichloro, meaning they're spaced one apart. So if we eliminate one side first, we're going to eliminate the other one such that they are in a conjugation, if at all possible. So either one, if either one of these eliminates first, the Zaitsev rule says that it's going to either eliminate with this carbon and hydrogen or this carbon and hydrogen. Once we do either one of those, we're going to end up with this as our intermediate here. Now, the good thing is that because this is our intermediate, we actually are going to now, once we form this, because it formed the more stable tri-substitute alkene, we're going to break Zaitsev rule, but we're going to make it work as the conjugated alkene such that we, instead of forming this tri-substituted isolated double bond and this tri-substituted isolated double bond, we're actually going to have, once one side forms, the other side is going to form in a conjugated fashion. So it's going to be double bond, single bond, double bond, giving us our conjugated diene. Okay. Now notice that this happens because the formation of the tri-substituted will happen first. It's lower energy intermediate, and therefore it's going to happen first. Once that happens, the second one's going to eliminate such that it's conjugated as your major product. So this one doesn't always let you use the Zaitsev rule for both. It only lets you use the Zaitsev rule for the first reaction, and then the second reaction follows the conjugation rule. Okay, so let's look at the mechanism of that to prove to ourselves that this is how it's going to happen. So either this chlorine here or this chlorine can eliminate first, and when it does, it will follow Zaitsev's rule and give us the more substituted alkene. The base is going to be pulling on this hydrogen to get it to go. The electrons are going to kick in, and then the chlorine's going to kick out, giving us our more substituted, our Zaitsev product. Okay. Now that we have that Zaitsev product, we have a competition between the Zaitsev hydrogen and the non-Zaitsev hydrogen, but it's going to deprotonate at the non-Zaitsev hydrogen so that we can get the conjugated diene versus the isolated diene. So these are isolated, they're not electronically connected. These have two sigma bonds in between these two double bonds, and this has one sigma bond in between those two double bonds, and therefore this is the less substituted but more thermodynamically stable and major product, and this is the more substituted, less thermodynamically stable minor product. All right, So let's take a look at that and see if they're on the same carbon. So that was one where the hydrogens were, I mean, the halogens were two um, carbons apart. What if they're on the same carbon here? Okay, this is called a geminal dihalide. In fact, you have both halogens on the same carbon. And what happens is what we'd expect, we would get the alkene elimination with the first dehydrohalogenation. And if we have a strong enough base, specifically this amide here, we can actually get a second dehydration to give us our triple bond. So this is how we can form alkynes from having a geminal dibromide. Okay, but what if they're not on the same carbon? What if they're just one carbon apart? We call this a vicinal dihalide, meaning that there's the one carbon and then one carbon over you have it. If you use the same base here, this is amide right here, we get the first elimination happens as we'd expect, and then the second elimination also forms an alkyne to get there. Okay, note this second elimination only happens if you have a very strong base like this amide reaction. So that means that and that's because the vinylic halide, the one right here that's on a double bonded carbon, is not very reactive. So we have to have a very, very strong base. If you have a weaker base like alkoxide or ammonia, this will not form the alkyne. You will stop at the alkene. Okay, so let's summarize all of our E2 mechanisms here. First of all, the kinetics are a second order reaction. Obviously, E, it's bimolecular, therefore the concentration of the base and the concentration of the alkyl halide are important. The mechanism is a one-step mechanism, bimolecular, okay? So the energy diagram is gonna have a single pump with the transition state being determining what the product is going to be. The more stable the transition state, the lower the activation energy, the more stable the product that's going to emulate that transition state, okay? It's favored with very strong bases. The better the leaving group, the faster the reaction. The bulkier the base, the more likely it is to pull off protons that are in the less bulky side, okay? All of these E2 mechanisms are favored in polar aprotic solvents. Remember, polar protic solvents are capable of solvating an anion and a cation. If you can solvate the anion cation, it's going to most likely form the carbocation. If you cannot do that, if you can only solvate one or the other, like in a polar aprotic solvent, you favor a bimolecular mechanism, okay? The E2 reaction is regioselective and stereoselective. The SN2 reactions often compete with E2 reactions, but you can force them to go to elimination reactions by increasing the heat, okay? There are no rearrangements because we do not form a carbocation, and the E2 reactions of alkyl halides are much more useful than E1 reactions because we do not have those rearrangements. Rearrangements would cause a product mixture. Product mixtures are not as useful reactions as if we can specify it's going to give one or two products versus multiple rearrangement products. Okay, and that is the end of chapter 7, section 3.